we might as well go ahead and get into the material. In a little bit of a review, let me remind you that I always bring more pins. Sometimes I leave them right here, and by the end of the semester, I'll leave them here in case it's like a backup, right? In case I forgot. By the end of the semester, I usually have the whole thing just completely filled. And then here's another thing. Now, usually these take a few minutes before they get dark, but it looks like this one wants to behave. Okay, so recall that separability, we're doing 2 dimensions, so let's start easy. Notice that I'm solving a flat potential. I didn't add any potential energy, so it's either 0 or just an EZ. What you end up with is a separated Hamiltonian. It looks like this. So they're separate wave functions. And this looks just like, these are one-dimensional. It's just that I've got this extra one. I got this extra one with a y in it. This little subscript is superfluous. I don't need that. Okay, what's a little funky, what's a little funky is when you have the situation, notice that I have partitioned the energy into 2 bits. I said that there is a part, as the separable Hamiltonian has many Schrodinger equations. Each is equal to its own constant. Of course, that constant energy. But then it has to be divvied up, right? Because there's only one total energy. So there has to be an energy in X and energy in Y. So it's safe to assume that, well, maybe this is like an even box. It's 50-50. Nature tends to do that. That's like the equal partition theorem from your undergrad thermodynamics. So it may not be hard to know how it divvies up. It's just 50-50. Or since you're the one characterizing a system, you should know this. If there's some division that becomes necessary in solving a Schrodinger equation such that you run into this problem, how things get divvied up might be a function of the system you're describing, so you should know this ahead of time. So if I ask a problem, I'd have to tell you. Anyway, of course, in the wave functions end up being some normalization constant, which I mentioned I forgot. You have a quantum number in X. Maybe the length in the X direction isn't the same as the length in the Y direction. I've used a paradigm where the box is centered at 000. So I'm not centering it. It's here's the box. So remember, particle in the box are easy if you don't, instead of centering it here, which case you get odd and even functions. If you just center it at the corner, it ends up being easier. Okay, anyway, so there you go. Why am I even talking about this? Okay, let's get back to our radial. We're doing the the damnedest thing is so crazy about this. The problem we're doing now, and it is centered at 0, which is actually the best way to do this. Okay, a particle on a 2D trap, if it's outside of this radius, that was awful, sorry, but if it's outside of that radius, infinite potential energy. We're going to solve the Schrodinger equation without the potential energy. We're going to get the wave functions, and then we'll apply boundary conditions. So like here you know that the wave functions are actually either the a x or y. I'll just put x. And then of course there's coefficients. So I screwed that up a little bit. That was awful, sorry. So this is what actually gets solved, and then the boundary conditions give you this. So we're doing the same thing here. We're going to solve the functions And they actually do look kind of, they obviously look kind of like this, except with an R. And then we're going to apply the boundary conditions that at a radius of A, as is traditionally used, at a radius of A, you have infinite potential energy. So, but before we do that, we're just solving the wave functions. Okay, last bit to mention, this approach, solving wave functions and then applying boundary conditions later, is, you know, that's how you do things when we're starting out with our simple problems. When we move to more advanced stuff, you'll never see this again. I mean, just mechanically how you work the problem. We don't do it this way. So there's boundary conditions, but it's not like you solve the functions and do the boundary conditions. They usually come together. So anyway, just pointing out that this approach we're taking, you're not going to see it again. It only comes up with these kind of, again, these are really kind of lower level problems. Okay, so where are we at? So last time, oh my God, I lost my place. We were converting, sorry, I lost my place here. Where do I want to be? I'll start out from the very beginning. So on your homework, you're going to, of course, derive the full cylindrical deal. And you really, I mean, as much as I mentioned last time, it's hideous, but on your homework, I broke it down into pieces that you really shouldn't have too hard a time with on any individual one, only to get this is the final result. So, you know, everything factors or things subtract, it's something like that. Okay, so anyway, and remember that this is actually, this is this. These are the same thing. These are the exact same thing. So if you ever feel like you're overwhelmed, I mean, it sucks how it's a little bit more complicated. And of course, when we get to 3D, this is 2D cylindrical. When we get to 3D spherical, it's hideous. I mean, this isn't that bad. Spherical, it's hideous. That goes across the board. But it's still this. What would this be? Okay, so now last time I mentioned we're going to multiply by constants, and you know, so I'm actually just repeating what I said last time. You know, I probably shouldn't take too much time on this. 2m. Okay, so I'm flipping that over, but I'm also multiplying by r squared, and I'm doing that for separability. So, and I also act on the left. Over. So remember that the separability mechanism is this. Act on the right, by the left, and what you end up with is it allows you to untangle the Hamiltonian to separable terms, and then it gives you the miniature Schrödinger equations at the same time. When you untangle the r's and the theta, the r's and th's in this case, that shows you that yes, it truly is separable. And having done that, you naturally then end up with the actual Schrödinger equations, the mini ones. So now remember, the problem is right here, not separable. R, T, together, in any form, on any term. If you see that, you're screwed. But again, this process unscrews you. And specifically when I multiply by r squared over h bar squared. So you just got to be clever about it. So here, let's do that r squared. And I talked about last time how the theta phi passes through these r walls, and then it gets divided out. So that's why there's no 1 over r phi. And of course, there's a 1 over r, wave function phi. There's a wave function of r because the one on the right is trapped here, right? This operator stops that from just popping over And anyway, and just let me know if you don't see that, because I hope that's actually really pretty obvious, but if not, just come by office hours, right? And R squared over R. Come by office hours, we can do it step by step. Okay, so as usual. Okay, now here, of course, on this term, this does not stop psi of r from coming over, so it gets canceled out here. The psi of b is stuck. It's stuck. It's stuck by that operator, that double derivative. Okay. Then no, that's not right, is it? No. Did I do that last time? I'm just doing over h bar squared. Did I get that reversed? My notes are reversed. What's that?
You have that different way.
Yeah, it should be this.
Yeah.
Right, you notice 2m e over h bar squared? Right, that k, or momentum vector, it shows up all the time. Only when you get to really advanced systems, do you not see that show up that way. You almost always see, yeah, there's an r squared or whatever. Okay. Now, here's the deal. Let me bring this over. So sorry about messing that up. So what I did was I just took this and I brought it over here, but I should have, I didn't multiply by that, I multiplied by 1 over that, so I screwed up. And then I should have recognized because 2me over h bar squared is something I see a lot. Okay, now, and one reason I brought this term to the left is because it's cool that it's positive, and the whole thing's equal to 0. And that's how mathematicians, when you look up answers online, you need to put it this way because this is what mathematicians like. Tell you what, let me put this one over here. I'm just changing the order. It's just, oh, but I forgot to multiply. No, that's right. Sorry, I thought I made a mistake. It's fine. Okay. So there's that, and then there's this. Derivative. Okay. And all of that's equal to 0. Okay, so I just wanted to reverse that because, as I mentioned last time, I see R's, and here is a phi. Okay, so separated. It's been separated now. Okay, now here's where things get kind of funky. Last time, you might wonder why I was talking about this, I divvied up the energy between the two minis. But I can't do that here because the energy is part of the radial, just funneled into it. I don't know why. When you do these multi-dimensional things, one of the dimensions becomes dominant. It is always the radial. It dominates over the others because it grabs the energy. And the others just are like spectators. I have no idea why it just wants to do that. I mean, I can certainly derive it. I just did. And here you go. All right, so now again, each one of these is a constant. And this constant is going to be minus that constant because, 1 minus 1 is 0. All right? So that I get. It's just that I don't know what the constants are. Because normally it's just, I can kind of get this, divvy up the energy into two parts. That I totally get, but you have no ability to do that here. Okay, so that sucks. Okay. Next part is, let's solve this one. And what are we going to set it equal to? So I've got a wave function I don't know, and what is it equal to? I don't know. Well, that's something, isn't it? Now this is the part that as I mentioned, I don't really like quantum too much. I've never been a big fan because there's a lot of hocus pocus that goes into this. I'm just going to do this and hope it works. which mathematically you would never do, right? Everything has got to be logical and follow and flow. But when you're in this classroom, all of a sudden kind of anything goes if the end result is fine. Okay, by that what I mean is, let's try, I'm going to try something that looks like a freeway. I'm going to actually, I think I have a substitute for that. I better do it right. Call that M sub L. Yeah, let me call that M sub L for reasons that will be apparent. Some consistency with some stuff that comes later. So that's M sub L. Actually, I'm calling it M sub L because it's analogous to Px, Py, Pz. M is -1, 0, +1, right? So you remember that from hydrogen. And you know that there's Px and Py and Pz, but they come about because the Schrodinger equation says that there's 3 p orbitals. For L of 1, which is p, L of 1 means your L of 0 is s, L of 1 is p. You have 3 p's because there's M sub L of -1, 0, and +1. Px, Py, Pz. So that's why I'm calling it M sub L. Okay. Now, what I'm proposing is to do this because what I have is the double derivative of a function divided by the function is equal to a constant. Now, that's actually what this is. Double derivative of a function divided by a function. I can just take this over here, would be equal to a constant. In this case, it's energy. Okay, so my e to the I whatever, e to the I kx, e to the I f e to the I something something is something that always seems to come up, and it does solve this. Okay, and so therefore, let me write this very quickly. So this would be equal to what? 1 over psi double derivative of psi is minus I m sub L squared. Right? Okay. So let me rewrite this all over again. Okay, so this is equal to minus m sub L squared. I'm trying to write it a little bit here. If this speed wave function e to the I m sub L v. So notice that while I am mathematically correct to stipulate that this is a reasonable wave function, look, there's a couple others. I mean, I could have used a sine or a cosine, right? But I'm just saying, yeah, it's kind of nutty, but this is how you do it. Anyway, it just kind of bothers me a bit that you just kind of pick something and go with it, and then, of course, we know we can take the predictions and test it. The test is perfect. So I guess I guessed correctly guilty. Okay, now here's the big question. What is all this equal to? Right, so notice that this part's solved. Right, remember, miniature separability, 2 wave functions. To solve the Hamiltonian needs to solve the wave functions. I got one of them. I'm going to make a presumption, then later test it, it'll be fine. I'm half done. Cool. But now I've got my other miniature Schrodinger equation, which is equal to a constant. What is that constant? Yeah, there you go. M sub L squared. Plus M sub L squared. All of this has to be equal to plus M sub L squared minus M sub L squared is 0. So yeah, I mean, it's not that bad. It all makes sense. It's just a lot. But I mean, plus 1 minus 1 is 0. I can get that. So that's nice. And let's see here. And see what there's one other thing. Oh, it turns out that due to this bothers me. Due to the fact that we actually have a boundary condition, by the way. You can go ahead and do a boundary condition. Let me dash that. We can go ahead and do a boundary condition, which is that, okay, so this of course is phi. Phi is this angle, obviously. So now it turns out that if you go 2 pi, if you turn about the whole circle, you better equal yourself. That's a boundary condition. The other boundary condition will be brought up in a moment. So remember I was telling you, you solve wave functions, then you do boundary conditions later. So we can go ahead and do the phi one, because we're basically done with it. Well, especially now we're done with it. Now what that means is the boundary condition then means m sub l is -2, -1, 0, 1, 2, dot, 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 dot. It's a whole number. It's a whole number, including negative. Now negative, all right, so this is like 1. This is -1. It can rotate backward. Clockwise, counterclockwise. So I get why there's negative. I get positive, but it's a whole number. The reason is because of this boundary condition. And if you do this, e to the 2 pi I 2 pi plus theta is equal to the e to the I theta. Okay, let me go back here. This is e to the, sorry, screwed up, my bad, let me start over, sorry. I just got ahead of myself, and notice I'm not looking at my notes. I m sub l, so you see what I did there? I screwed it up pretty royally. Then we get e to the I m sub l 2 pi e to the I m sub l d is equal to e to the I m sub l b. Okay, so what you get is this e to the I m sub l 2 pi better equal 1, obviously. Now you go look up Google exp parenthesis I 2 pi parenthesis enter 1. E to the I 4 pi parenthesis Google says 1. E to the minus 2 pi I Google 1. There you go. So m is a whole number. So that's how you know that. Now, I noticed some of you were kind of looking at me cross-eyed last time when I was talking about these factors. So on your homework, I'm forcing you to get familiar with how to interpret this correctly, if you haven't seen it before. So anyway, look at the homework and just do that last problem, and you'll get this. You haven't seen it before. Okay. Anyway, why am I still talking? Oh, anyway. The reason I'm doing that is, right now we have to solve this thing. And it's kind of more important than this one. This one is it's really stupid, right? There's not much to it. But this one's it's a little bit more complicated, and it's got the energy, which is kind of what we're really trying to do. Remember, to solve the Schrodinger equation means to get the wave functions, but then what you really are after is the energy. So with the wave functions, you get the energy, right? So this guy's kind of important. Now, it turns out that I need to know that m sub l is an integer. That's crucial, right? Because all of this is equal to that. So I kind of have to know what that is. That's why I went through all that rigmarole. It's also very good that it's an integer. That helps solve it. Okay, so what is that? Let me write that down. Let me wipe out the board. And now this is the part where it gets unsatisfying. And we tend to do this in this class. I am going to go look in a 17th century, 18th century textbook because this equation was solved then. Most of these were solved around the 1800s when calculus was invented. They did a lot of stuff real quick when calculus was invented. Okay, I'm going to write all that down again, just so it's a little bit neater. You know what we're doing. Hopefully I won't flip anything over. And I'm not sure why Okay, what I'm doing here is I'm taking I'm taking this part, setting it equal to Isabel, and I'm multiplying through by the wave function. Yeah, I'm just multiplying through by the wave function. And where you'll see that is right here. And notice I brought Isabel over to the left, that's why it's squared. Okay, there's my Saya bar. There it is. Sorry, man. This is still, okay, I like that because that's K or K squared. Okay, there we go. All right, now all we have to do is be savvy enough at DiffyQ to solve this. By savvy enough at DiffyQ, I already said Bessel's, this is Bessel's differential equation. So whenever Bessel solved this, I don't remember, I'm not kidding, I'm sure it was 1800 something. This is Bessel's equation. You're going to notice it is identical. I'm going to make a slight change just so you, you can translate a little bit, understand the nature of the solution a little better. Okay, this is how Bessel's equation appears in the literature. Okay. And the reason I bring this up, this is called the order. It's an integer. So we already know that Isabel is an integer, so I can already see minus something squared times psi. The order is Isabel. Now, the reason we're calling, why does this get a name? Because what you have to do is, what Bessel did was, if you plug in 0, remember, Isabel can be 0. It's 0, 1, 2, 3 are including minuses. If you plug in a 0, it's a different equation. Right? I mean, it's like one of the terms just disappeared. That's a different equation to solve. The thing is, when you have these deals, you have to solve each one separately. So when that's 1, that's 2, that's 3, each one has to be solved separately. That sucks. Now, it turns out mathematicians can figure out recursion relationships. In other words, if you figure out the first one, there's like a little formula to figure out the next one without actually that formula not being solving this. It's something else, like just multiply it by I to the order. It's something like that. Actually, I'll show you in a minute. So there you go. Okay, so these are called, the solution is called J. It is universally called this J alpha. I'm going to say it's a function of R. Okay, now notice again, you see the order. Okay, this is what this thing looks like. Now, Bessel solved this. There's ways, like cheap ways of figuring these things out that with like Taylor series. And so that's what Bessel did. So you have a sum. So here's your Taylor series, right? There's an infinite number of terms. So we're going to have, unfortunately, something called M. I should have probably picked a different letter. That's a gamma function. I'll explain the gamma function in a minute. And you don't need to know this. I'm writing all this down just so you see it, but you'll never really need to know this. And the reason I'm showing this to you is, I'll explain in a minute. Here's our order. So here's how the order gets in the problem. Oh, M plus alpha plus 1. So you can see, yeah, this is awful, right? A gamma function is this. Now, as for how any of this in this argument is whatever, so we call that Z. Well, here it's M alpha 1. So M alpha 1 is Z now. And it ends up being this integral. Now, as for how this is the solution to that, ask Bessel. I don't know. So there you go. Okay, big picture. Bessel has this thing, figures out for every alpha, solves it, and then realizes that basically it can be done this way. This rather not terrible thing. Somehow this integral shows up. Good for it. Okay, now let me ask you this. Can you deal with something like this? What do you think? Let me ask you a better question. All right, so it turns out if you go into Matlab and say, hey, Matlab, Bessel, it's called Bessel, the Matlab function. Bessel J, you give it the order, let's say 0, and then a number, like 2. You give it a positive number because that would be, you give it a positive number because that would be the radius. Then you hit enter, and then it spits out the result. Anyway, so Matlab does this. Now, have you ever done anything like this before? A lot of you are saying, no, yes, we have. Okay, so get their calculator. Tell me, what's sine of 0.3? What's that? So I'm just kidding. You get my point, right? It's just a function. Just like sine. What does your calculator do when you say sine? Okay, if it's sine of pi, it may be pre-programmed to say 0. It may be pre-programmed to say 0. But if you plug in sine of like 0.1, what do you think it does? Anyone have an opinion? How does it give you the number?
Is it based off of Taylor series?
It's a Taylor series. Yes, it's a Taylor series. Sine has a Taylor series form. And a calculator takes it out to you can actually look it up. It's part of your documentation. All calculators tell you how many Taylor series terms. It's usually like 8. It's part of the manufacturing part of the calculator. I can tell you that. So this is no different than a sine function. You just haven't seen it before. You got to tell. All right, so this is like sine or cosine, 0 or 1, and then you just tell it what the number is, and then it spits out a value. That's all there is to it. Okay, I'll show you what these look like. I'll show you what these look like now, and then we'll graph them. I'll graph it with the phi part. So that's what the Matlab's for. We'll go ahead and warm up the projector. Okay, so this is what it looks like. Now it turns out that J of 0, this is S-like. So this particle in a cylinder, or particle in a sphere trap, they're really similar to the hydrogen atom. They're not the hydrogen atom because the hydrogen atom has a Coulomb potential. But short of that, which is kind of important, it's actually really similar. So you're going to have, that's basically your two angular momentum. 0 for S, 1 for P, 2 for P's. Kind of makes sense, right? Oh, and you can have more than one of them. Okay, so this is S-like. J of 1 is P-like. Okay, so I'm plotting this on the y-axis. And here's R. Okay, so this is J of 0. And this is this is around 2.4 on the r-axis. This is around 3.83. Yeah, they go on forever, of course. This is 5.52. 2. This is around 7.02. Go on, little wiggles. Now, if you remember your hydrogen atom, you may recall that S states are finite at the origin, and P and D and F and G states are not. So, so there you go. The S-like state, just like a hydrogen atom, is closer to the origin, closer to the nucleus. There's not a nucleus here, but you get the point. The P states are a little further out. They're higher in energy as a result. Now again, you don't have a Coulomb potential, but you're seeing really similar behavior. Now, let me also, you don't need to write this down, but where a particle in a sphere and a hydrogen atom are different, is that the hydrogen atom is more like that. So you do see, that's the S state. The 1s state looks like this, and of course the 0s state for particle in sphere looks like that. Anyway. Okay, so hopefully you're familiar with that. Now, when it comes to applying this, so that looks all fine and good. Hopefully that's not mind-blowing. But really, it's a three-dimensional thing. And that was weird. It's a three-dimensional. What the hell is that? You hear that? There's some echo. Okay, this is real funny. You can see my email. Probably stuff from the cat bed. So anyway, I do have. Oh God, you kidding me. Sorry about this. I had it set up. That's what I did when I came in here. Oh, you're fired. Okay, so I have this code written. If you can see, unfortunately, it is really that's what. Okay, so this includes the angular part too. And there you go. Look at that. What the hell is that? Okay. So this is the actual S state. Actually, I'm kind of shut up now. These computers are almost useless. So what you're seeing here, when I plot the S state being at the origin, is you're seeing that if you can imagine just looking at it, up the center and down the side, it looks exactly like that. And again, all I've done here is add in, there we go. I've added in the angle parts. So and you'll be doing this as well, if that looks cool. Let's plot the P state. Oh, you may notice, look, if you look at my code, Bessel J, right here, right? Bessel J0, R, S state, Bessel J1, that's a P state. So there's one of them. There you go. Now, another way to think about this is that this is basically the low harmonics of a drum. So, you know, quantum mechanics is something that's very visualizable. So this is like, it's like PXPY, right? So this is orthogonal. Let's see if I can. Okay. Sorry, this is just unbelievably annoying. So what has happened here is that they have really been cheap and put in the cheapest computers possible, which things barely low. Okay, so I just wanted to show you that when it comes to the angle parts, there we go. So now you can see of course how things are orthogonal in this type of space. Okay, anyway, I hope that was kind of neat. In your homeworks, I'll show you how to do that as well. That's in the Matlab. Okay, last bit. This will be on your next homework. It turns out that this stuff here is pretty important when it comes to semiconductors. This is how you describe the electronic structure of a semiconductor quantum dot. So what happens is you get, say, like a 2 nanometer particle, and of course it's a semiconductor. What happens is when you shine light on it, you get an electron in the conduction state. The electron is the particle, and the dot is the sphere. Now, what happens is that it gains kinetic energy by being in a small trap. Now, what happens is that the wave function, let's do the lowest energy excited state. That would be the S state. So we can forget the P state. And the boundary condition forces it. So now we're doing the boundary condition. I want to give you like a very definite application. Okay, so again, here is the Bessel S state. Bessel is the particle in the sphere. This would be the lowest energy state for a particle in the sphere. The particle is an electron. The sphere is a semiconductor quantum dot. And the boundary condition says the wave function has to stop at the boundary. And of course, that's because the potential energy on the outside is infinitely high. Okay, now, what this should do is affect the energy, but how? The way that this happens is actually, I have to admit, I have not been honest about this. It's actually, I didn't want to blow your head off, it's KR. Now, here's how you know that. All this stuff, you can't have an argument. You can't have units. You can't have units in the argument. Just like E to the IKX, K is designed to negate X's dimension. X is meters, K is 1 over meters. You cannot have E to the unit. You cannot have E to a meter. That's nonsense. It's scientific nonsense. Now, Bessel stuff does the same thing. It's not R, because R has units of meters. You can't feed this function a unit. It's nonsense. Based on the mathematical form, just trust me on that. This cannot have units. So the actual units are KR. Okay. So notice how the quantum confinement deal shows up in this electron trapped in this. Okay, it'd have to be a disk. Sorry, I'm using a battery now. Tomorrow we're going to do particle in the sphere. Today we're doing particle in the disk. You can't make disk-shaped semiconductors. So sorry, bad analogy. Anyway, so I shine light on a semiconductor disk, and I get an electron. Okay. Now here's how this works. Okay, for the lowest energy state, you have to have Kr equal to 0 at R is equal to A. Remember, A is the boundary. A is the radius where the thing stops. Okay, I won't look before in a second here, because this is real easy. Now remember how the Bessel function is 2.4? Okay, so at R equals 2.4. So what you end up with is, now you know that K of course is still 2me over h bar squared times the boundary has got to equal 2 over 4. See that? Because this Kr goes into the Bessel function, and the lowest energy state has to equal 0, which requires this to equal 2.4 based on this graph. All right. You follow me? I know there's a little circuitous. Lowest energy state for particle in the disk, let's start there. 0 at 2.4, the first 0, The boundary condition says you have to be 0 at the boundary. The boundary is at r equals a, so kr is equal to 2.4. Because over here you get 0 at r equals a. Notice then that you can now solve the energy. Energy is, okay, 2.4 over a, those will both be squared. Each part squared will be 2. Okay, so there you go. Now this is where the whole, you've all heard of quantum dots, right? This is where they're size dependent. As it gets smaller, the energy goes up. If they're infinitely big, then there's no effect. This is technically a kinetic energy effect. So the whole semiconductor technology deal works by changing the kinetic energy of electrons. When a nanostructure, when a semiconductor nanostructure gets really small, there is an additional kinetic energy. Remember, this is kinetic energy. I never really included potential energy. Not really. So this is kinetic energy. So when semiconductor nanostructures get really small, the carriers pick up extra kinetic energy. Now, this fundamentally, in terms of like why is that important, it changes the electronics of this particle. And maybe this particle is part of a CPU. So, in fact, Intel, they're always making things smaller and smaller. Now, of course, you can't make things smaller than an atom, right? So there's a logical limit to their chips. They can't be smaller than atoms. But here's the deal. It turns out this effect means that they're actually at their limit. They're almost at their limit because the electronics of their devices change due to quantum confinement. That if they make them smaller, they actually have, you might think, oh, well, maybe they'll work better. Sure, something changes, but they change in a way that they don't work better. In fact, they're pretty much at the limit right now. They cannot go smaller because quantum confinement messes up the electron's energy such that the devices actually stop working. So we're now at the limit of our CPU technology. All right. Anyway, so that's all I got. Sorry.